By now, we have met quite a bit of examples of how that operator, that symbol, comes about in gradient, in directional derivative, and in many other places. And it's time to look at this more closely. So what you see here is a formal definition of the Nabla operator. And what you see here is probably one of the first examples of an operator without an actual object yet it works on. So it's just an operation with a potential to do something. So you have partial derivatives and associated unit vectors. And then you leave the possibility to apply that operator, this operation, to something. Why we're looking at this? Because that is a very useful way to apply this in many situations, not just for the gradient. So this is in 3 dimensions and this is in 2 dimensions. So the difference is just that you have only 2 partial derivatives because you have only x and y directions. And we've seen how that works with a gradient. We just apply that operator to the f, which is a scalar field, and we get a gradient, which is a vector field. But in fact, that's more general than that. We can almost think that this operator itself is a vector. So even though it's a derivative without a function, but because it has 3 components, it is a vector. And we can use that to translate lots of things we know about vectors to this operator. And we can use this for lots of situations, as you'll see in a minute. Let's look at some of these properties. First of all, it has a vector property because it has vector components, but also it has a derivative properties because it involves partial derivatives, or in some sense you can think an analogy to the ordinary derivative. So for these properties, let's take just any scalar fields, let's call them f and g, and let's take just a constant lambda and another function of one variable h. So these are the properties. If you take this operator and apply it to the sum of 2 scalar fields, so you kind of take a gradient of a sum of 2 scalar fields, it's the same as to take a sum of the gradients. So you take a gradient of a sum of scalar fields and you get a sum of 2 vector fields. Then it's the same. So it's again, you might think there's a linear property like you've seen it in the Laplace operator. And of course you'll expect another property, that if you take a scalar field and multiply it by a constant, just a number, just fixed number, then you can take this constant outside because derivative doesn't act on that, and that's another feature of linear property. Or you can take a product rule very much similar to what you would do with the derivatives. You take this operator, apply it to the product of the scalar fields, and then you can convert it into a gradient of the first scalar field multiplied by the second. So that's will be the result of this as a vector field. And then you need to do the complementary operation where you take the gradient of a second scalar field to multiply by the first. So it's again very similar to what you would do with the normal derivatives. Or you can do a quotient rule, again very much analogous. You take a ratio of the 2 scalar fields and then you apply the same rule you would do for the derivatives. Or you can take a chain rule. So let's say that you take this operator, this Nabla operator, apply it to the function of the scalar field. And then what you do, you apply chain rule. So you first take an ordinary derivative of that function with respect to f, and then multiply it by the gradient of that scalar field, which is again, a total result will be a vector field. So you see that that is a rather general way how you can translate what you learned about derivatives on one end and about vectors on the other end, and use it together to apply to a new situation. And the reason why we thought about this operator, this nabla, in somewhat detached way is because it allows us to introduce other differential operations on the fields, in particular on the vector fields. So that is very useful. So now that we have an object, this nabla, which behaves somewhat like a vector and somewhat like a derivative, we can use it to define operations on vector fields. And we will look at two operators. One will be called divergence, one is a curl. And that is precisely what we're going to consider in the subsequent videos using the nabla operator.